A developer gave an LLM a multi-step planning problem and told it not to think. And the results were more accurate than any chain of thought prompt anyone had tried before. Here's the problem. LLMs are terrible at multi-step logic. Not sometimes. Consistently. You ask one to plan a sequence of actions with hard constraints, dependencies, ordering, resource limits, and it hallucinates steps, skips constraints, or confidently gives you an answer that's just wrong. Chain of thought helps a little. But it's still the model guessing, dressed up as reasoning. This project does something structurally different. Instead of asking the LLM to reason through a problem, it asks the LLM to write a Prolog program that encodes the problem. Then it hands that program to an actual Prolog interpreter, a symbolic logic engine that has been mathematically correct since 1972, and lets that engine find the solution. The LLM becomes a translator, not a thinker. And that changes everything. Let's look at what this actually does in practice. You give the system a natural language task, something like, schedule these 5 jobs on 2 machines, respecting these dependencies. The LLM's job is to read that and output valid Prolog facts and rules. Things like, job 1 must precede job 2. Machine A can only run one job at a time. That kind of structure. The Prolog engine then runs the query. It doesn't guess. It either finds a valid plan or it tells you there isn't one. No hallucination. No confident nonsense. Binary, deterministic output. In the repository, the author uses Google's Gemini model as the LLM backend, and SWI Prolog as the symbolic engine. The integration is surprisingly lean, a few hundred lines of Python that pass prompts in, parse the Prolog output, run the interpreter, and return results. You can see in the demo queries that it handles things like route planning, simple scheduling, and dependency resolution with clean, verifiable answers. What surprised me was how well the LLM handles the translation step. Writing correct Prolog from scratch is genuinely hard. But the LLM isn't being asked to be rigorous, it's being asked to be a decent first-pass translator. And it turns out that's something these models are actually good at. Pattern matching natural language to a formal syntax is much more in their wheelhouse than multi-step logical deduction. But here's the thing, this setup has real ceilings. The LLM can and does generate syntactically broken Prolog. A missing period, a mismatched functor, an undefined predicate, and the interpreter throws an error instead of a plan. The current implementation has some error handling, but it's not robust. In a production context, you'd need a validation layer between the LLM output and the Prolog engine. The second limitation is scope. Prolog is powerful for constraint satisfaction and logic programming, but it's not a general execution engine. If your problem involves numerical optimization, probabilistic reasoning, or large state spaces, Prolog will struggle. This approach works best when problems have clean declarative structure and many real-world planning problems don't. Third, the prompting is fragile. The system depends on the LLM consistently outputting Prolog in a specific format. Slight changes in phrasing the input, or switching to a different LLM, can break the output format entirely. There's no schema enforcement, no grammar-constrained generation. It works reliably in the demo cases, but it hasn't been stress-tested against adversarial inputs. Now, what could this realistically become? The most promising direction is combining this with structured output enforcement. If you constrain the LLM to output only valid Prolog using something like grammar-based decoding or a fine-tuned model trained specifically on Prolog generation, the error rate drops dramatically. A few research groups are already working on exactly this. Pair that with a richer suite of symbolic backends, not just Prolog but also answer set programming solvers or SAT solvers, and you have a genuinely composable planning engine that doesn't hallucinate by construction. Enterprise scheduling and logistics is the obvious domain. Any system where a human currently writes rules manually, compliance checks, workflow automation, resource allocation, could potentially use this architecture to accept natural language updates and translate them into formally verifiable logic. That's not a toy use case. That's a real gap. So why does this project exist? Because the AI field made a wrong turn when it decided that scaling language models would eventually fix their reasoning failures. It hasn't. Logical reasoning is not a language task. It's a computation task. Language models are compression engines trained on text. They're incredibly good at pattern matching, translation, and synthesis. They are not theorem provers. Prolog, and symbolic AI in general, got abandoned in the 1990s because it couldn't scale to unstructured data. But it was never broken as a reasoning engine. It was just limited in what it could take as input. LLMs fixed that input problem. They can read anything a human writes and translate it into structured form. The combination LLM as interface, symbolic engine as executor is the architecture that actually separates these two concerns correctly. This project is a small, honest implementation of a big idea. It's not production ready. The error handling is minimal, the prompting is brittle, and the scope is narrow. But the architecture is sound. And frankly, seeing it work on even simple planning cases is more convincing than any chain of thought benchmark I've read. If you want to follow where this kind of neuro-symbolic hybrid is heading, subscribe. Next episode we're looking at a project that uses a similar pattern but replaces Prolog with a SAT solver for hardware verification. Same philosophy, completely different domain, and the results are wild.